Good. Let's. I hear that. A horn honking outside of the office. All right, here we are. So we left off with Bitcoin script, and we're done with that now, right? We now understand Bitcoin script, how coins are transferred, and that solidifies our base level understanding.
Mm-hmm.
We're now looking at this contract, and we ran through a very basic few things yesterday. We know about these props now. They're stateful props on a stateful contract.
Mm-hmm.
And we know we can make assertions about the outputs of a transaction. If we can make assertions about the outputs of a transaction that, for example, makes sure that a contract survives and continues to live into the new transaction, right?
Mm.
How might we use that to make a multi-party contract that can survive and be updated by different people at different times? Just speculate on, thinking about, okay, well, we have these tools, right? What could you try to do with them?
So you're gonna. So
We have an output that gets created by the original contract.
What's the goal here?
To make a contract that maybe Alice could update, then Bob could update, then Charlie could update, and then back to Alice, and then back to Bob, and then all the way, anyone can update it. But whenever they do, it has to keep living, right?
Yeah. Okay, so your spend methods or whatever they're called.
Public functions.
Could have different requirements that aren't constrained to a particular public key, for example, or allow multiple keys.
Mm-hmm. Alice or Bob.
You can say has to be paid public key hash or whatever of Bob or Alice or whoever.
Mm-hmm.
right. Okay.
Right. Or even different public methods which could be used by different people.
For each one, yeah. Okay.
So there's that, right? And then those public methods have to make sure that, less some state update or some counter. Let's take a look at a stateful counter contract that's got a little bit less in it, so we can actually think of the easiest possible stateful example. So there's you should check out, and you can, sCrypt Inc. boilerplate.
Right.
So people should check that out. There's a bunch of contracts in here. So once again, you have an artifacts folder, which isn't included here, but once you compile it, you would see it. And then SRC contracts is the main one. So there's a lot of contracts in here, guys.
Wow.
What we want, you can even do, lots of contracts. Voting, Zor, puzzle, price bets, I don't know, BSV 20, mint basic, but counter.
Which folder?
So GitHub, it's sCrypt Inc. boilerplate, and it's SRC contract.
Okay.
And so we're going to go to counter, if I can find it.
Next one, yeah.
Counter, right. So we're importing assert, byte string. Let me read this to make sure. Yeah, this is true. Right. So this is very simple. What is this contract saying? Why don't you run through?
Okay, so, yep. If we go through, the counter is what we extend the smart contract with. We've then got a prop, and it's obviously got true because it's stateful. We've got a big int, which is the count, which is going to be incremented. We then go into the constructor, which is very simple. We call the super with our arguments, and then we set the count. So that's to start with. We're just setting the count to start. So is that actually, did we pass that in, or was that just, let's have a look up there. No, it's just a value at this point. Yeah, okay, the constructor, yeah, we passed it in. Yeah.
Or a new instance, yeah.
Yeah, for each new instance. Right, okay. And then our first method is just incrementing it. So we put this dot increment, and what are the constraints? Do we have any constraints? Any asserts? Nope, no asserts there.
One at the end.
Oh yeah, that's. Oh, yeah, okay, at the bottom. I was only going down. Right, and so we set the amount. Make sure the balance. Oh, okay. So we're actually setting the amount there. Oh, we've gone into the pre-image to go and have a look at it and get the amount that's in there. And then we're doing the outputs, and we're saying that it's a byte string, which is build state output. So that is that's not a method. That must be where's build state output?
Building the new locking output. Great. Plus the change output.
So change output I want you to ignore.
Right.
We're not going to use that in Babbage, I don't believe.
Okay. And what about build state output?
Build state output, or at least I don't believe, maybe there will be change outputs, but I'm not very familiar with that yet.
Right.
I don't think we should use that
Okay.
for our initial one.
Yeah.
But a state output, right? If you actually, and we're using this inside of R1 too, so let's just hover over this to see the docs. Build state output. So it says that a built-in function to create an output containing the new state. Its input, the number of satoshis in the output.
Right.
So that's going to actually create an instance of an output that needs to be in the transaction.
Right.
So in our case, we're saying, all right, this is the output. This is a new output that I expect to be in the new transaction.
Right.
And then it's saying, in my case with the coin flip, right?
Yeah.
Think about this. Alice puts in some value when she constructs it on line 46, right?
Mm-hmm.
She's going to make this output script, and then she's going to put, we talked about there's no representation of satoshis in the output script when you first create it. But then when Bob, so we talked about cancel offer yesterday, we'll go into accept offer. When Bob accepts, he needs to, reveal a number, and we'll get to that later, but times 2n on line 77. What is that saying?
Every time its value doubles.
So, the state can only be 0. We can see on line 67. So the one time that it is valid to call this, right?
Yeah.
What are we going to do? Now let's run through this, right? We're going to assert that the state is 0, right?
Yeah.
Make sure Bob's signed.
Right.
Right? Make sure that Bob is either revealing 0 or 1. So the way the coin flip contract works is Alice creates 0 or 1, then Bob creates 0 or 1, and then they're random, and then Bob doesn't know what Alice picked originally. And then Alice reveals, and if they match, Alice wins. If they don't match, then Bob wins.
Oh, okay. Yeah.
So that's how the coin toss works. But in this case, Alice has already kind of committed to a hash of her value that Bob doesn't know. But it's a blinded value, meaning that Bob can't know what Alice did. But Bob is now guessing, a number and trying to be different than Alice without knowing what Alice did. So a 50-50 shot, right?
Yeah.
Bob has to pick 0 or 1. So that's what that assertion on 71 is. Then we actually do some some instance variable, member variable assignments. So saying now, Bob's number is saved in the state of the contract, right?
Yeah.
And remember 74, Bob's number is actually true, right? If we look at stateful on line 38. It's true, meaning it sticks around. That's what that means.
Right.
So, and we're also making the state 1, right?
Why do you have to set, you're saying this.Bob number equals Bob, or you're setting it to the one that's passed in? Okay.
Right, that's what the number Bob picked when he accepted the offer.
Yeah, okay, that makes sense.
To accept an offer, he has to pick. And then, why are we setting these on 74 and 75 before we call 77?
Because that new output has to contain the state of the current contract.
Right, which is that. Right.
So that output that's built is based on the current contract, right? It's locking script and everything?
Yes, which is incorporating these mutations. Now these are already in here.
Yeah.
Now this dot, these things.
If you did it after, then it would have an old state.
If I did it before.
Makes sense.
Yeah, right. If I built the output before I updated my state variables, then the output would be based on old state.
Okay.
So we're doing it in the right order here. And then, what is the significance of 77, though, beyond just making the output have the same script, or having the correct script? Beyond just having the correct script, what is 2n?
It's doubling the amount.
The value.
Not only does Bob have to...
Yeah, because they both put in $1 or whatever.
Right. So whatever Alice put in, Bob has to double.
Yeah.
Right. So not only does Bob have to create the correct script, but he also has to double the money.
Yeah.
And then we take the hash
of the
output.
original values from Alice, right?
So here's an output declared 77. Why are we hashing the outputs on line 78?
Because they're going to be used as our key to unlock the padlock, aren't they?
Well, yeah, but why would we have to hash the outputs?
Well, what's our SigHash?
Well, let's look at the top. It's got to be up here, so there's that one.
Single.
Line 65.
Okay.
So we're using a SigHash single.
We have to include the hash of the outputs. And
so what is the
new output to add.
Because
so I'm assuming it doesn't have its that hash hasn't, or the hash doesn't automatically change, I assume. And so since we're adding a new output, we probably have to manually update that, maybe?
You're not updating it, but you're checking it, right? Bitcoin script doesn't update pre-image or anything. It
checks it, yeah. Okay.
Right? But what is in the pre-image? Is it just the outputs in the pre-image? If I go look at the pre-image again. Right?
Yeah.
Number 8.
So yeah, we have to hash them.
It's a hash of the output. So you can't, you have to hash because the pre-image contains a hash of the outputs, which of course in the case of SigHash single is only the corresponding output, right? So the delegated next output of this contract, that's a use of SigHash single, right?
Now, can you zoom back in? Does that go?
Here?
Yeah.
We got the accept offer.
Output equals hash. So, state output. Accept output. Does this return a unlocking script? Is that right?
Does this public method return one? Yeah. When you invoke it properly, remember call pub earlier? Well, yesterday.
Yeah.
We'll get
I
back
was just trying to see how the output actually got included, but I guess it's because you're saying this dot, so it must do its internal thing.
Well, think about this. When I create this transaction, and actually go to send it to the miners, right? The unlocking script that would unlock the previous output, would that script succeed if I neglected to actually include the output, which reflected in hash outputs? Would my signature pre-image be correct?
No, because you're doing the hash single, so you have to.
Right. Yeah. I'd have to include it, right? If it didn't include it, suppose I actually have a thing here in operations.ts. accepting the offer. How does accepting the offer work? Well, we've got a challenge here, and it's got to do this, and we're going to get the offer transaction. We're going to do some things we'll get to later. But I'm going to, call. I get my unlocking script. Basically, let's jump down to 297 and ignore everything about it, right? I get my unlocking script by calling the accept offer public method, right? And then I use that unlocking script and create action. Create action 345.
345. Yeah.
And my output here is the next output script. And the value on 360 is 2n.
The next output script, okay, you're manually setting times 2 there.
For the Satoshi's value.
Right.
Now, what if that wasn't...
It wouldn't work.
It wouldn't, yeah.
This wouldn't unlock, right?
Are you talking about that amount?
Well, this
I see, yeah.
spend couldn't happen, could it?
If the output's creating value?
The output it's creating value is less.
Because that amount is in the preimage, right?
It's in the preimage.
Right. So you've got to update it inside the preimage.
We passed it in on line 77.
Yeah.
For the locking script.
Yeah.
For the new hash outputs, for the new output, the state output has to have this amount in it.
Yeah.
It built a
Not
state output.
Not necessarily the unlocking of the previous, but I guess it's in the...
Well, it is because look at the assertion on 79.
Yeah, okay. Because it's in this method, then I guess it's constrained to it.
Yeah.
So now you understand a bit about stateful contracts.
A bit, yeah.
You can make things that live for a long time. Right? Now, after this happens, Bob has accepted the offer. Where does that leave us? Can Alice now take the UTXO that Bob just created in his transaction? And can Alice use line 59
What's 59?
after with the new UTXO?
Hang on.
No, because the contract state updated. So the number wouldn't be there anymore.
Line 75 is important.
Oh, I see, yeah.
If you
Yeah.
don't do that,
Yeah, then it could use the one above, yeah.
it could. So only in state 0 can Alice cancel the offer. If Bob spends accepting the offer,
Yeah. Yeah. Then that's
then Alice can't go back
nullified.
anymore.
Yeah.
Alice is now bound by this contract that she created for herself and Bob. She can't get her money back anymore.
Yeah.
Now let's get into how this coin flip contract actually works. Why is there an Alice hash up here, do you think? In the constructor. Why would we need that in this contract?
In order to confirm that data provided by Alice is...
In order
To sign it, yeah. You need
in order
it.
for Alice to commit, right, to some value that she can't go back and change later.
Yeah, so we have that hash and we verify it later.
Yeah.
Right. Now, do you know what the SHA-256 hash of 0 is, or could you easily find it? I mean, I'm not asking you to memorize it, but could you easily find the hash of the number 0? If you wanted to,
Is this a trick question?
No, it's not.
Yeah, because you can hash anything.
You could easily hash the number 0,
Yeah,
right?
sure.
Yes.
And you could easily hash the number 1, right?
Yes.
Yeah.
So if Bob knew that Alice hashed the number 0, he could check, right? And he could say, well, I want to win, so I'm going to pick 1 as my number.
So he'd be able to check that she hadn't cheated then, so...
So how can Alice stop Bob from cheating? think of the answer? How could she make a hash that only later she would reveal the value?
42.
So the Bob card just checks the hash of 0 or the hash of 1.
Either.
You could do a hash that requires some sort of data to be revealed.
Some type of...
Type 42, is it? Type?
You could use 42. No, not type 42. No. You could
some key, right?
Yeah. Some
key.
Some secret thing that she has to reveal. Let's look at how Alice reveals the winner on line 84.
Isn't that an HMAC or no?
It's similar. It's a simpler version of an HMAC. You know, we could use an HMAC actually. If we had that functionality in sCrypt, which maybe we do, maybe we don't. But look at what I wrote here on line 84 and in this method. Walk me through what's happening in this method. This is the crux of the coin flip contract, right? How is this contract working? Why is it fair?
So we take Alice's nonce, which is that random value provided,
right?
Plus Alice's number,
which she now has to reveal, right?
Okay. And we hash it. That's the hash for verification. We assert that equals this to Alice hash. Is this from Alice's side?
Mm-hmm.
Okay.
So Alice originally constructed this contract at the very beginning.
Yes.
And that state, Alice hash, propagated forward because, line 26, prop true, right?
Yeah.
So it survived all the way through Bob accepting on 66, right?
Yeah.
Now Alice hash was propagated all the way forward, and Bob saw what Alice hash was. Bob doesn't know what Alice nonce was until now.
Oh.
Right? But
Okay,
now...
So now she's revealing. So now he can check that hash actually equals the one that Alice originally gave him.
Mm-hmm.
It included Alice's number, so he knows she didn't cheat and switch that number.
Mm-hmm.
And then he checks those numbers.
Yeah.
And let's see, Alice's number is 0 or 1, so it has to be one of those two cases.
Mm-hmm.
Then we go down, we say make sure Bob's number, or if Bob's number is Alice's number, then...
then who has to sign?
Oh yeah, then Alice...
Now we know this is the number.
Look at the comments as well.
Picked.
Yeah.
If they are the same...
Because Alice... The same Alice wins, the other way is Bob.
Mm-hmm.
Yeah.
And the winner signs.
Mm-hmm.
Meaning the winner gets to decide where the outputs go. Right?
Yeah.
Mm-hmm.
Right.
All right. So, you guys think you have a solid understanding of this contract? I think.
I'm getting a feel for it.
Right. Ask questions if you have them. Let's run through this and make sure that you understand what's going on here. It's a stateful contract for a coin flip between Alice and Bob, right?
Right.
So suppose Alice, let's think through all the ways that people could cheat, right? What are some examples of ways that a malicious party, Alice or Bob, might try to dupe each other? In this, hey, let's flip a coin kind of context.
Hey, Bob, I'm gonna pick. Or here's my number. I'm picking 1. Actually, I'm picking 0.
Mm-hmm. All right. So just directly saying, here's the number, and then, oh, joke's on you, it's the wrong one. Okay, so why is that method of cheating ineffective? How have we mitigated that method of cheating by Alice?
We included the
hash.
secret nonce,
Mm-hmm.
that as well as the number that we're hashing.
Mm-hmm.
So that if either one of those actually changes, the hash wouldn't match.
It wouldn't match. And so what line number is making sure that Alice can't do that to Bob?
The assert.
The assert,
hash for verification equals, Alice's hash.
Because if it was just the number being hashed or something, then Alice would still have to send the number. Wait.
If it was just the number being hashed, who could cheat?
I think so. Alice, let's say she hashed her number and sent
Well,
it.
yeah, because if it's a 1 or 0, then we know what the hash is. Bob would know what the hash was, so
Bob.
he could. Yeah, so he could cheat.
And Bob wouldn't know what the number is, or he would. Oh yeah, because he would just check the hash like we said. Okay.
Right.
Yeah.
That makes sense.
So Bob could cheat, right? If Alice just hashed the number,
Yeah.
Yeah.
because Alice would be revealing her hand
Yeah.
prematurely.
So we want a way to conceal the number that Alice picked while also still making sure that Alice has to stick with the number that she picked.
Right.
Mm.
That's called a blinding scheme. Very important.
Right.
Yeah.
All right. So that's one way that Alice could cheat by, joke's on you. I changed my thing. So we stopped that by using a hash, right?
Mm-hmm.
And then we stopped Bob from cheating that because
We added the nonce.
we added the nonce.
Right.
We're blinding him from what the actual.
Right. That's important. So now he can't guess because he's not going to guess that really long nonce. Right? 32 bytes long or something. I mean, he can try. How long is it going to take him?
Yeah.
Long time.
Longer than the age of the universe.
Mm.
Multiplied by the number of atoms in the universe in units of years, right?
Right.
So anyways, not going to happen. Okay. How else could they cheat? What if Bob just never accepted the offer and just said, "Ha, your coins are locked now. Bye. See you later."
We have to have a time.
Well,
A timeout, don't we?
maybe not for that. I mean, we might. That could be.
We
one
just
way.
have to have. Yeah, you could time out though. You could have time for Bob instead.
Yeah. Well, that's important. That's later. Yeah, but
Yeah.
what if originally, right? It's very simple. Alice made an offer.
Yeah,
And
Alice just needs a way to get it back.
yeah, right. So one way that Bob could cheat, if we don't prevent it, would be to just do nothing. Just drop off the face of the earth and say, joke's on you. You lose money.
If I have
Yeah,
to
back,
lose,
right?
you lose too.
Right. Well, Bob doesn't lose anything.
No.
Because,
Well, he doesn't win either.
he hasn't put anything in.
Yeah.
Alice has. So that's why, why do we need line 59?
Yeah. So she can cancel. Yeah.
If Bob doesn't respond after
Yes.
a time, right, then, Alice can just cancel.
Yeah.
Now, if Alice could cancel any time, why is that bad for Bob?
Because he's put money in.
Right, so if he already accepted the offer,
Yeah.
then Alice can't cancel anymore.
Yeah, but we've accounted for that with the contract state.
We have, yes.
Yeah.
That's why contract state, and that's why this method here,
Yeah.
59. So now we're getting somewhere, right? We're stopping these people from cheating.
Yeah.
All right, so suppose that here's a really hard one. Suppose that first Alice makes an offer, and then Bob accepts the offer, locking Alice in.
Mm-hmm.
And in so doing, Bob publishes his number. So now Alice knows that Bob published his number, right?
Mm-hmm. But she's
And
already.
Alice knows the number that she's already committed to.
Yeah.
So now Alice,
Neither can
maybe
get
she
out
now
of it.
knows- what is it?
Neither can get out of it now.
Neither can get out of it. You're right, because it's accepted now.
Yeah.
It's been committed. There was an offer and there was an acceptance, so that is done.
Yeah.
There's no going back from that, right? But
Yeah.
so someone's going to win, right?
Yes.
But what if Alice realizes that she lost?
Doesn't matter.
Therefore, instead of being cooperative and calling this function on line 84, what if she just says,
No.
because I lost, I'm just going to not let you take your money, and I'm just going to never reveal my knots and just go away.
Bob gets to take it back after a certain amount of time.
That's right. So there is one more way to unlock this
Right.
contract. If Alice just goes away and drops off the the earth on line 84. Doesn't do that, because she's not being an honorable... Mm-hmm. And think of the implications here. Yeah. There's a record on-chain permanently of, publicly at least, not permanently, but publicly at least, of what Alice chose to do. Did she choose to lose like an honorable person? Or did she act stubbornly? Now you know who you're dealing with, what kind of person you're dealing with. And the last resort is down here. Right. So,
yeah.
What are the constraints in place on this?
Yeah, well, obviously, it has to be that they have both agreed, so that's your contract state 1.
Contract state 1.
Yeah. And then you just check the signature for Bob, and check that's valid. And then finally, we have our time lock. Right, okay. So if it expires, then what actually happens? So Bob wins automatically. Okay, yeah, because he's just signed it. Yeah.
All right.
And timeout is set in the constructor or something.
By Alice originally, they all agree on it at the beginning.
Oh yes, up there. Okay.
Because there's no way to mutate certain values after the constructor has been run, even though they are all
sets the timeout?
What is it?
Who sets the timeout?
Who creates the contract at the beginning?
Alice.
So Alice?
They have to agree. So Bob is just agreeing it by actually accepting her offer.
Right.
Yeah.
By line 66, Bob has done his due diligence, hasn't he?
Yeah.
What if Bob
know what the timeout is?
What is it?
How does he know what the timeout value is?
Well, it's part of the contract. It was constructed in the constructor.
Yeah. So it's up to Bob to look
at
that.
The timeout is set to like 10 years, and Alice is like, haha, you don't get it for 10 years.
No, but he would have accepted it, wouldn't he?
You're not checking it, though.
But yeah, I think you do. It's up to you to check the contract if you're
not checking it, but do you want to sign the do you want to go forward or not, right? Are you going to touch
Where's
this?
that checked, though?
It's not checked in this contract. It's not checked on chain, is it? Why would it be checked on chain? Why would the miners do that due diligence for Bob?
No, it's up to Bob to either he acknowledges that he trusts Alice, or he has to check the contract himself, which is why it's available, why it's actually the code is actually there.
Okay, so you're saying that when it makes sense to do like assert the timeout value is less than whatever. Okay.
No. Why would the miners nanny stand? Why would they do a babysit? Why would they babysit these people?
Just checking.
Hang on, this is what happens in Ethereum, isn't it? Why people get rugged, because...
This isn't a lesson about Ethereum, and I won't speculate on Ethereum.
No, okay, sorry.
But...
Yes.
But yeah, we don't do that in this contract, because when Bob sees what Alice proposes, when Bob sees that locking script that Alice has created with these stipulations on it, with all of these terms and conditions...
Yeah. But this...
If Bob accepts something, and he signs on 66 with a signature, which is here.
Yeah. But
if you sign something and you didn't read the contract, what happens?
But this does mean that all the Bobs of this world are going to have to understand how to read smart contracts.
Well, sure. Or they're going to have to use applications that act as fiduciaries to their interest.
Agents or,
Right. I think it's, they're agents. They represent the council. Right. Why do we have lawyers?
Yes, I get what you're saying now. You're saying, yes, you say like, whatever the higher level code is, it will say, if timeout is acceptable, then accept the offer.
Yeah.
And if your lawyer lies to you about what's in a contract, can you go back on that contract? You can prove that your lawyer lied to you?
No, you can't go back on it. You have to actually sue the lawyer, surely.
Yeah, could be. Yeah. I mean, you get compensated though, right? You say, look, this lawyer breached their duty to me to give me a straight answer about what this was. They misrepresented everything. And so if an app doesn't represent things properly in a contract, then the app developers are liable.
Mm.
The parties engaged. The apps are the agent of the user now.
Okay. Interesting. Yeah.
So before calling line 66 of this code, Bob needs to look at that timeout value and make sure that it's acceptable to him.
Yeah.
Because if it's 10 years,
then
Alice just involuntarily locked Bob's coins in a hod locker type locking thing for 10 years.
Yes.
And he has to wait 10 years. He would have to.
Yeah, but
you can do that.
But there was no signal associated with it, so it's pointless.
Oh, yes, there was. Yes, there was. It's right here, right? It's right here on line 54. Line 54.
Yeah, but no, that's not a signal. No, I'm talking about a signal for the world.
Oh, I see. It's
yes. Yeah.
Well, the signal is Bob is a really unintelligent.
Not you, Bob.
No, just
not
a Bob.
No, but you see what I'm saying?
Yes, we understand.
Right.
What's like the general guidelines for determining if particular constraints should be checked in a contract, like on chain, or in some higher level application?
It's
I know we've done both. With push off and all that. And it seems like sometimes it's a little bit ambiguous trying to figure out if it should be in script or if it should be a higher level.
Does it facilitate the exchange between parties?
Between multiple parties, not just like one individual.
If I want to shoot myself in the foot, right? Then the miners do not stop me from doing that.
Yeah.
Do they?
No.
Yeah, you can just lock up your coins and never get them back.
Right. I could send 1 million Bitcoin into private keys that I'm irresponsible enough to even hold on to.
I thought we weren't going there, but yes.
I'm not going anywhere. I'm just saying that someone could do that. And then the miners, are they going to stop me? Are they going to say, no, this is a bad idea. Don't do this. No, they're not going to do that.
No. They're just, all they care about is being paid.
They just do what the transaction says.
Yeah.
They look at the code, they do it. So the miners are not going to save you, ever. If you think the miners are going to save you, no. They're like a notary or a witness.
Yeah.
These contracts that we make with Bitcoin are peer-to-peer. We sign them. And we also notarize them.
Yeah.
What is the form of the notary? What represents the notarization of a contract after it has been duly executed in Bitcoin?
Well, the signature, the fact that you have actually put your signature on it.
That's the signature. Right. But when you sign a paper document, public notary stamps it after.
Oh, okay, stamp, yeah.
What is the form of the notary stamp? Stamp is an important word. What is the form of the notary stamp?
Is that when it's included in a block?
Yes.
Yeah.
It's the Merkle proof.
Right.
Right?
Yeah.
By putting something in a block and fixing it in time, you say, we, the notaries of this world, public notaries, notary public, right? Witness this thing happening. If I want to sign a document, suppose I want to sign a will that says that in this will we're going to have 3 people pull numbers out of a hat, and that's going to determine how my possessions are split up after I'm dead. And maybe it's a very poorly written document, it's got grammar errors, it's got all these problems, right?
Okay.
If I want to sign this, and I go to a notary public, and I'd say, I'd like you to witness me signing this document, right? Are they going to stop
Nope.
No, they can't.
All right, looks good. See you signed it. Good to go.
They're going to say, I see that you signed this.
Yeah, give us the $100.
Right. Give us the fee. I see that you signed this.
Yeah.
Thank you for your business.
Mm-hmm.
Same with the miners. The miners will never save you.
Nope.
And that's how it works. So the answer to your question about what goes on chain is, what terms do you stipulate with respect to the people with which you are dealing?
Okay, maybe another way to put it too is, so you want it's not necessarily just the data, because in both cases the data could go on chain, but it's like the rules or like the conditional check.
It's the opcodes, really.
The assertion, right?
Yeah.
Because you could put the data still on chain when you're using like push data.
You could do that.
But then I guess it's the checking of it, the validation, all that it would be not on chain. So it depends on if you want that.
Right.
Yeah.
The assertions.
Mm-hmm.
There's assertions in all these methods.
Yeah.
Every sCrypt method must have at least what?
One assertion.
One assertion, and it probably should be at the end. There's never a point to doing anything after an assertion, unless you're going to make another assertion in a public method of an sCrypt contract.
Right.
Because why would you, right?
Yeah.
No valid reason to make any code after an assertion.
Unless you're going to do another one. Yeah.
There's going to be another one because, why?
Because it doesn't have any effect. It's only assertions that actually have an effect.
Right. That's how you write contracts.
So
what
they're,
if I...
so they're effectively clauses, aren't they, in a contract?
Or the way I described them previously was they're like obstacles in an obstacle course that you can only complete if you check off all of them.
Yeah, within a method, yeah.
Programmable money.
Yeah.
Do you have a newfound appreciation for what that term actually means?
Yes.
What does programmable money mean? Either of you.
You got it, Bob.
You've got to... It means that you can make contracts between people, peer-to-peer.
Right. And is it peer-to-miner-to-peer? Do the miners...
No. You can just ignore miners. They don't have any effect as far as you're concerned.
As far as the rules of the contract.
The rules, yeah.
Right. They witness things. Now, if I try to spend the same coins twice...
Oh, they'll stop that, yeah.
They'll stop that because... Why?
Well, because that's what they check. They actually...
Right.
That's their job.
It's
to witness and always to stop double spends.
It's always fraud to double spend.
Yeah.
If I, as a notary public, do not verify the identity, meaning if I let someone sign off the same title, the property, the two people.
Yeah.
Suppose I have it notarized that I sold my car to one person, and then I also sign that same car to someone else the next day.
Yeah.
And they go to the same notary. Aren't they going to look at me a little weird? Did you sell that car yesterday?
Yeah. But they probably won't do anything. I mean,
the police will do something. Though,
yes.
Right? Miners enforce rules. They do enforce the double spend.
Yes.
But they only enforce the rules that are written in the contract and prevent people from committing fraud that way.
Yeah.
So it's a system that is really efficient at stopping people from committing fraud against one another. And that's important.
Yep.
In the world, actually.
It is.
So now you understand stateful contracts. We can run through, we ran through all of the methods of this contract. Now I want you to run through and describe from top to bottom, if you can, Bob, I think you did the last one with the counter. So, Braden, you get the harder one.
All right.
To run through this contract, what are we importing? What are we using? What are we doing? How does this contract work?
We import in some useful functions and classes and things from sCrypt TS. We go down, we have our one export default, which is our class, point-flip contract, which extends the base class smart contract. Then we have our properties of this class, which are stateful, so they have @prop true. @prop denotes these are properties and their types.
And what properties do we have, and why are those properties included?
So 256 for Alice's hash timeout, which is big int because we can't use primitives, or we
right.
Yeah. So we have to use big int or big int's what's the string one?
Yeah, byte string.
Byte string, yeah.
Byte string.
All right.
Yeah. So we got those types there on each of those, and then just go through each of the properties and briefly describe why each of them are necessary to effectuate this contract.
Alice's hash is necessary to provide Bob with some information that he can later validate the number that Alice picked to make sure she wasn't cheating.
Right.
Timeout is useful for Bob and Alice both agree when this contract will timeout, at which Bob can claim the coins if Alice just leaves them hanging. Alice's public key is denoted there. Bob's public key, the two parties in this coin flip contract. Then we have Bob's number, which is the number that Bob picks. And then we have the contract state, which keeps track of whether or not Bob has accepted this contract.
Right.
And we proceed to the constructor, which initializes this contract with those values that are passed in, such as who is Alice, who is Bob, what is Alice's hash, the timeout, contract state, which defaults to 0. It's the starting state, and then Bob's number.
Initially, these numbers are kind of empty.
Defaults.
They're not.
Yeah.
They don't have to be initialized by Alice at the beginning. They're kind of preset defaults before they're used. Right, so we assign all the variables, and then there's one
super constructor passing those same arguments so it can use it how it needs to. We assert that Bob's number is 0 or 1.
If it's provided.
Right, it's provided.
Is that actually oh, it's default negative 1. No, remember we added this yesterday? You can see my blue line or my green line here on the end of line where it's 48 here.
Oh, yeah.
I should remove that.
Yeah, because Bob's number isn't provided at the beginning, right?
So let's just go back to how this was before I, made that change.
Okay. So we go through and set those.
Right, and now we'll go through each of the methods.
Okay.
And just describe why each one is useful, why it's necessary, what the parameters are, and then what it does.